Hi everybody, this is Dr. Bricker here with a little bit of background information about the photoelectric effect lab. So it's in Learning Materials, week 16. It'll be our last lab of the semester. And it's right here, photoelectric effect PhET lab. So the way to submit it, if you can't get it to upload, once you're finished with it, you could submit it here, browse your computer wherever you saved it, and upload it. That's the easiest way for me, and then once I grade it, I can send you back the graded copy. But if for some reason you can't get that to work, just you can just email it to me. Just maybe put in the section, the information section, like Physics 221 Lab or something like that. Okay, so let me open it up here. And it's a PhET simulation. It's a pretty good lab. I think you're going to actually like it a lot. So it deals with the photoelectric effect, which was from chapter 28. It's the idea that you shine electrons on metal and you can liberate the electrons from the metal, put that in part of a circuit, you can get current to flow. Okay, so kind of like this. Here's a photon that's got some energy and it's heading across. So what we can use is a potential difference to stop this from happening. So the first part is just kind of the theory part here, where the work, so delta W here, that's the work, is equal to the voltage difference times Q, if I were to multiply both sides by Q. And it's an electron volt here. So first question, how much potential difference or stopping voltage would be required to stop an electron that has this much kinetic energy? So this is the kinetic energy it has. What sort of stopping voltage would stop the electron from going across? So if you take this much kinetic energy, turn it into electrical potential energy, what would the voltage difference be? And if you're familiar with electron volts as a unit, that's a really easy answer for you. Okay, similar kind of idea with the second question. Part 2 is the actual PhET part. So first part, sort of just the background information part of it from chapter 25. And then part 2 is where we'll actually use the PhET. So just a little bit about this table. This doesn't mean divided by A. This means the units are A. So here, that means the units are amps. So current when voltage is 0, and the unit's already given. Stopping voltage, this means that in volts. And then this is the energy that you would calculate in joules for the kinetic energy that the electron would have. So the energy that the electron would have here, the kinetic energy that the electron would have in this column, is equal to the potential energy that we have, the electrical potential energy. So if you have the stopping voltage, multiply it by the charge, that's the potential energy that turns in, the kinetic energy turned into that when you actually stop this from happening. Okay, so let's look at the PhET real quick, and then we can come back and look at the rest of this. Now you do need Flash to use this, so I'm using Firefox with this. The newest versions of Chrome won't work so easily with this, so I would just try using Firefox. And sometimes they just open right up for you, these PhETs, but this is a Flash-based one. So I'll have to download it. So save file, come up here, and I've opened it a couple times today. Executable file, so I'll just hit OK. And it looks like this. So you can't make this screen bigger. I haven't found a way to do it. Right now the intensity is set at 0. So if I want to, I could do options, show photons. Right now there's no photons, but the idea is, here's a light source. I can change the wavelength of the light from this. Right now it's on 400 nanometers, which is violet, but I don't have any shining. So let me put the intensity at 50%. So those are photons. Okay, 50%. So photons come here, hit electrons. Some of them grab onto that energy and they go across. Right now the battery's set at 0 volts, but we do have current flowing. So the freed electrons are moving across. They end up at this plate, and they don't like to be by each other, so they head through here. So right now this is basically a short. There's no voltage on the battery. And we have a current of 0.071 amps. So stopping potential means, how do I stop this from happening? The way that the battery's set up right now, I'm not going to be able to. This is actually negative charge. This is the positive side of the battery, although it's set at 0 right now. So I've got to make this voltage negative. So if you notice, I move the cursor to the left here. So now this plate is negatively charged, and I have less current. I'm down to 0.018. Let me go back to this direction. I was at 0.071 or so, it looks like. Yeah, so let me make this voltage negative. Okay, so at negative 0.8 I don't have anything, but maybe maybe I don't need quite that much. I'm at negative 0.06 here. So you could actually click here and change this by hundredths. So let me make it negative 0.061, and I still have whoops, enter. Okay, that's not enough. Let me make that bigger. Negative 0.062. Okay, now it went down, so I'm getting closer. I'm going in the right direction. You don't want to overshoot it. I mean, if you made it really negative, you're not going to get anything. But I want to get to the point where I'm just stopping it from happening. That's the stopping potential. Okay, so negative 0.63 volts. There's a data table that we'll go back to in just a minute. So at negative 0.63, that's the stopping potential. That's where you get no current to go. And if you notice, the electrons are going back the other way. Some of them don't even make it across. None of them go through the circuit here. So what's happened to the kinetic energy when they get over here? Well, it's turned into electrical potential energy. So the charge of an electron times the magnitude of this stopping potential, that's how much kinetic energy they must have had. And then what you're seeing here is sodium. So the target here is actually sodium. So a metal made of sodium. You can change this. I don't think you have to for this experiment, but we'll just use sodium. Okay, let's go back to the lab real quick. The write-up. Okay, so we've opened it up. Put show photons. Very good. Here's the link. If you can click it, or you can copy it, whatever you want to do, put it into another browser. So sodium, that's what we were just using. Wavelength, again, that's units. Wavelength, nanometers. So 400 nanometers, that's where we started with the violet actually. Intensity 50%. Current when the voltage is 0, that was so current when the voltage is 0. Okay, so put the voltage at 0, see what you get, and then stopping potential, that's when you actually change the battery. So stopping potential means that there's no current. So adjust that like I did till you get no current. Write down the magnitude of that voltage here, and then calculate the energy that the electron has in joules. So that this column here would be the charge of an electron, the magnitude of the charge of an electron, times the magnitude of this voltage. That'll give you the kinetic energy. The reason is electrical potential energy came from somewhere. It came from kinetic energy. Okay, good. So then you'll increase the intensity to 75 and do 100%. And then there's some questions to answer about that. Okay, so I don't want to give too much away with that. Okay, and in this lab we're actually going to be able to calculate the work function of sodium. You can look it up, but we'll actually calculate it too. And we'll calculate Planck's constant from this lab. So the next part here, we will use 125 nanometers. Again, that column's wavelength, the units are given nanometers. So go to 125 to calculate the frequency. It's the speed of light divided by the wavelength, and you'll see why we're getting the frequency in just a minute. Same thing, get the stopping potential. That's where the current is 0. Calculate the energy just like we did in the first part, and then increase the frequency to 300 the wavelength to 300 nanometers. Calculate the frequency, adjust the voltage until you get 0 amps. That's the stopping potential. Figure out the energy here. That's the charge times the voltage. We want it in joules. Okay, so you'll have to do a little bit of experimenting here and fine-tune the voltage stops here. As you can see here, go up by 0.01. You actually have to click in the box and change it to do that, to get fine control. Okay, and then we've got a few questions here. Something about the cutoff frequency. Okay, good. I don't want to say too much about that. I'll give it too much information away. A nice little blurb here about Einstein. The other part of part A here is, in other words, light travels as a wave and behaves as a particle at the same time. Name 3 observational phenomena that clearly show that light behaves as a wave. So think about what we did back in chapter 25 when you answer this. There's at least 3 ways from chapter 25 where we looked at the wave behavior of light. Okay, good. One difference with the notation in this lab, the work function, they're using phi. We just use E sub naught for the work function in the chapter. Phi here, it's the same thing, it's just different notation. So when you see phi, that means the work function. Okay, so work function, if you remember, it's Planck's constant times the cutoff frequency. Okay, so once you get that information, that data table that you just had from 4, we want to make a graph of this. So using the data in number 4 up there, graph the maximum kinetic energy versus the frequency. So maximum kinetic energy over here on the vertical column, and frequency here on the horizontal column. So if you want, you could do it in Excel or some other program, get that information. Now if you want to, if you make a nice graph, if you can figure out some way to attach it, you could put it right here, or go old school and just, you have what you got from Excel, just kind of sketch and annotate the graph below. Okay, so I would recommend doing it with Excel and then getting a nice graph and then kind of just you putting that information onto this graph. The reason to do that is to get the slope. It's a lot easier to get the slope in Excel or some other graphing program that you might have. So what is the value of the slope? What does the quantity represent? So let me show you a little bit about that. Okay, I've just scrolled down to the bottom of this just so I can write something out here. So from what we saw before in chapter 28, the maximum kinetic energy, this is really the photoelectric effect idea. It's the energy that the photon has minus the work function. I'm going to use the same notation as the lab. This is the work function. Okay, so what you're going to do is make a graph of, I don't know if I've got enough room here, on this axis the frequency, on this axis the maximum kinetic energy, and you're going to get some kind of a line. So this is already in slope-intercept form. Y equal mx plus b, right? Because you've plotted the frequency on the horizontal axis, which you usually call x. So the role of x is being played by frequency. The role of y here is being played by the kinetic energy. And then the intercept, that's what b is, the intercept is the work function. So whatever comes in front of x is the slope. Whatever comes in front of frequency is Planck's constant. So when you do this lab, you'll actually be able to make a nice graph. The slope of it is Planck's constant, and you should get a pretty good number for that actually. Just be kind of careful when you're getting your stopping potentials. So lots of little moving pieces with this lab, but I think it's you're going to have some fun with it, and you're going to get a pretty good number. Now, if we were still in class, we would do this lab, and you'd also get a pretty close number. We would do a similar thing to this. So there's no big write-up. Just go through, answer the questions. You'll have to create this graph, do a little bit of calculations, enter some questions, and then upload it through that link. If you can't get that to work, then you can just email it to me. And you can work on this as a group, as I said all along. That's perfectly okay too if you're still in contact with your group members. Okay, email me any questions, and this will be due, I believe it's on Wednesday of finals week. I think that's May 6th, actually. So hopefully you'll knock it out. This is the last one. You got about 9 days to do it. Okay, talk to you soon. Bye-bye.